Bismillahirrahmanirrahim. Assalamualaikum and very good day to you all. In this video, we'll talk about chapter 8-9, Statically Loaded Tension Joint with Preload. This chapter is taken from the book Shigley Mechanical Engineering Design, and the pictures taken here is from the book itself and from the Google Images. Okay, so the tensile stress and yielding factor equation 824 and 835 represent the forces in a bolted joint with preload. The tensile stress in the bolt can be found in equation 83 as this is the stress for bolt. Stress B equals to FB, force on the bolt, and area of the thread equals to CP plus FI per over AT, which is CP is the fraction of external load carried by bolt, P is the external tensile load per bolt, Fi is the initial bolt tension, At is the thread, okay, area of thread. So this is like this, okay. The force given by the clamping force, okay. The force Fb is the force given by the clamping force that you want to preload. The P itself is the external load given by any factor. Like for example, I I I knock this whiteboard with my hand. The force from my hand is P. This is the external load given to the bolt behind this whiteboard. So this is the external load. Okay. And AT is the area of thread. This is the area of thread. Okay. And thus the yielding factor of safety guarding the static stress exceeding the proof strength is NP is the yielding factor. Okay. SP is the proof strength given by the catalog from the bolt. Okay, when you buy the bolt, it should have the catalog, and the catalog will tell you what is the strength of that bolt. Okay, and this is the stress on the bolt. Okay, this is the SP equals to strength of the proof strength of the bolt itself, and CP, CP is the fraction of external load, P is the external tensile load, Fi is the initial bolt tension over the area of the thread, and the yielding factor of guard is this equation SP AT over CP plus Fi. So actually in this topic we want to study the uh, the statically stress factor on the load, meaning that uh, if the load, okay, if you are giving the load, okay, let's say you put the bolt like this, okay, it becomes static, like your table, like your chair, like your cupboard in your hostel, like your hostel bed, okay, it is static. Okay, whenever you go to holiday, your chair at your hostel, your table at your hostel, nobody using it. Okay, and then they are sitting static. Okay, and we want to study what is the load on that chair, on that table, so that the bolt can withstand the load. Okay, let's for example, you are putting extra load on your table. Okay, let me draw this table. Okay, this is a table. Okay, and then you put load, extra load on that table, and then you go back to holiday. The semester break, you go back to holiday, then suddenly you come back from your holiday, this table broken away, this table broke. Okay, okay, this table become cracked, the bolt cannot withstand the load given as the extra load, okay, this bolt, this table crack away. Okay, this is what we want to avoid. In the end, you will find the suitable diameter for that bolt. Okay, let's say you make a wrong design, you choose a bolt with uh, with the shorter diameter. Okay, maybe this table cannot withstand the load, and it will fail at the bolt. Okay, it will fail at the bolt. So that is what this topic we want to talk about when you are putting the stress on in static. Okay, you are putting the stress in static, not moving. Okay, your part is not moving. Load factor. Since it is common to load a bolt close to the proof strength, the yielding factor of the safety is not often not much greater than unity. Another indicator of yielding that is that sometimes it used is a load factor, which is applied only to the load P as a guarding overloading. Okay, applying such load factor and L to the load P in equation A, equating the proof give this equation. So remember this equation is actually without an L. An L is the load factor. The original equation is SP equals to CP plus initial load Fi over area of thread. So this is the original equation without we putting the load factor. So now we have to put the load factor because we do not know what load we want to put. Okay, so we put an L here. So we put an L here, and L is the load factor. So time of the CP. Okay, in front of CP. So okay, and solving the load factor give an L equals to SP AT minus FI C over CP. Okay, whatever the load you want to give, load factor you want to give is up to you and up to the design and what decision you want to put on the on that design. Let's say for example, the closest to you that you have seen, you will see it every day is the chair, the major, the chair, the table, the bed, hostel chair. Okay, all everything that you have seen every day. Okay, okay. This is a bed. This is a chair, maybe a table. Okay, you do not know what you want to put. Maybe let's say this is a bench. Okay, okay. And then you design for one kali person, one person. Okay, and then for the load factor, it can support two person. Okay, maybe if you put the 3 person or 4 person, this bench cannot support, and then it will break break away. This is the relation of what I want to uh, I'll try to relate with the load factor. Okay, load factor guarding against joint separation. If you remember in the previous slide, I gave example of a table and a chair. Okay, given extra load, that chair, that table cannot withstand the load. It will fail at joints. Okay, it may fail at joint or it may fail at the middle of the table, middle of the chair, middle of the bed. Okay, so now in this slide we are talking about load factor guarding against joint separation. So the purpose of uh, screw and bolt is to join. Okay, join something like this. Material A and B, you want to join. Okay, by a bolt. Okay, this is a bolt, this is a bolt. We want to join it. So load factor guarding against it become separate. It becomes separate. This is the load factor. We want to put the value so that we want in the end we want to choose what is the suitable diameter, suitable material, okay, to choose to avoid it to become separated. Okay, so the load carrying capacity, figure 818 in the next video, in the next slide, okay, is the stress strain diagram of good quality bolt material. Notice that no clearly defined yield point, and the diagram progress move up to fracture, which corresponds to the tensile strength. This means that no matter how much preload is given to the board, is we retain its load carrying facility. Is what is what keeps the bolt tight and determines the joint strength. So pretension is the muscle of the joint, and its magnitude is determined by the bolt strength. If the full strength of bolt is not used in developing pretension, the money is wasted and joint is weaker. What does this sentence mean? Okay, it means that when you tighten the bolt, okay, when you tighten the bolt to its maximum, when it reaches its maximum, that you cannot tighten anymore. Okay, then it is the preload. It is already preload, and it is the maximum force that you can give, and the load given by that bolt, whatever force given to that bolt, even you take a machine, even you take this power tool to tighten it up, okay, doesn't give any extra load given to it. Okay, you just retain the load carry capacity, and furthermore you must give the maximum force, maximum preload to tighten up the maximum that you can. Okay, because it's not it's no use for this bolt. The bolt does not reach its maximum capacity, and then uh, the joint is become weaker. Try to understand what I'm telling about. Okay, uh, remember to tighten up. Okay, like my mark here. If I when I put whatever the force I given by my hand, okay, even my stronger friend have if I give to my friend who is stronger than me, he try to put, also the load carrying is the same. Okay, the same. It cannot go anymore. This is called the load carrying capacity. This is the figure 818, the typical structural diagram for both materials showing proof strength, SP, uh, yield strength, SY, ultimate strength. Okay, so you remember from your study in year 1, you are study about the stress strain diagram. Okay, this is the elastic part, meaning the part can come back to its original position, like this rubber band. Okay, I pull it up, and you go back to its original position. This is called elastic. Okay, and then this is the yield strength. Yield strength. Okay, this is the proof strength, meaning that ultimately it can reach like that. So this is the ultimate strength, and beyond this is the ductile region, fracture region. It may fracture. So giving extra load, the your bolt may damage. Okay, good quality bolts in plastic range. What does it mean by good quality bolt in plastic range? First of all, what is plastic range? Okay, you remember when you learn in year 1 in material science, you learn about elastic plastic. This is elastic. When I release my hand, it will go back into its original position. But what happens if I stretch more? Okay, if I stretch more, this rubber band will elongate, and then we cannot go back into its original position. In this graph, stretch strain graph, okay, this is the region of elastic region of elastic. Okay, okay, any part, as long as it does not deform, it is in the region of elastic. So like this, I try to bend this panel, it cannot bend. Okay, when I release my hand, it go back to its original position. This is called elastic. Okay, and this rubber band I stretch and I release my hand, it come back to its original position. It's in elastic region. So the plastic region is when you elongate. Okay, this is the plastic region. When you elongate more, it cannot go back to its original position. So just a tips to you, sometime in your everyday usage, okay, you see plastic every day. Okay, your plastic bag, okay, your plastic bag, you have to go to the grocery store. Okay, they give you plastic bag. This that is plastic, of course. Okay, but in engineering, the plastic is defined as something else. Okay, the plastic meaning in engineering, uh, things that cannot come back to its original position. It is no, not like that. The plastic is when it is moving slightly. It's just a simple definition like that. Okay, so uh, this is plastic. Okay, meaning that if you give extra force, extra load, and you are strong and you give extra force to it, this bolt, the nut, the thread in that bolt, it become the plastic region, meaning that it surely it becomes stronger. Okay, uh, and it increases the principal stress, and maybe nobody can tighten out it. Okay, so this torsion is held by friction of the bolt head and the nut. In time, it relaxes and lowers the bolt tension slightly, meaning that given time, that bolt will be relaxed. Okay, and it becomes smooth again. Okay, so as a rule, a bolt will either fracture during tightening or not at all. Okay, so if you fracture the bolt, then you can see with your eye that the bolt is fractured. Replace the bolt. Okay, replace that bolt. If you see in your eye it, it does not fracture, then your bolt is safe. Your structure is also safe from damages. Do not rely on wrench torque. Okay, this is the wrench torque. In the last slide, in the last video, I talked about wrench torque. Do you have already calculated in an example to calculate the range, the torque, and you give the torque value to this range, and this range will you can do the wrenching with the predetermined torque. Okay, but as a tip, do not rely too much on the range torque, because it is not a good indicator of preload. Actual bolt elongation should be used whenever possible, especially with fatigue loading. In fact, if high reliability is a requirement of the design, then preload should always be determined by bolt elongation, meaning that the bolt, okay, the bolt when you are tighten it, okay, it may elongate or it may shrinkage. Okay, measure it. Okay, you have to measure it, uh, especially when become with fatigue loading, meaning that you may put your part, you may put your product in static position too long. Okay, like the bench, like the chair. Okay, whatever things that you put it statically, okay, doesn't go anywhere, it become fatigue. Okay, it become fatigue at a long time, so bending will happen, everything. Okay, so we want to avoid it. Okay, this is try, you are do use the rainstorm, but do not rely on it too much. Okay, Russell, Burstall and Watt. Okay, RBNW recommendation for preload are 60 kpsi for SA grade 5 for non permanent connection. You can read this statement. Okay, so this is the recommended for preload. So initial force is 0.75 force for preload. For permanent joint connection, use fastness, and this is 0.9 FP for permanent connection. Okay, where FP the preload obtained from equation. So if the bulk, okay, the bulk you have to use again and again, uh, take this 0.75 for initial load for preload, and then if you the bulk you not use anymore, but it's a permanent connection, use 0.9. Okay. Okay, recommendation on preload here, as P is the flow strength obtained from table 8.9 to 8.11 for other materials, and approximate value is SP equals to 0.85 SY, yield strength. Be careful not to use a soft material in a threaded fastener. For high strength steel bolts used as structural steel connectors, if advanced tightening method are used, tighten to yield. Okay. uh, you can read it. You can see that B&W recommendation on preload in line with that we encountered with digital and everything. So what is meaning by tighten to yield? Meaning that you tight until you cannot tight anymore, and use extra force to make it tighter. Okay. This is what they recommend in preload. Again, in the previous slide, you should remember there are one statement said from this book said that if you can see it with your eye, your board is damaged, then replace it. Okay, the board cannot withstand. Okay, but if you can see with your eye, the board nothing happened to the board, uh, you can tighten it uh, as hard as you can. Just to make sure your component is structured, has structural integrity. Nothing can happen to your product. That's all for the video. For this video, see you in the next video. We are going to do an example 8.4. Thank you very much.